The next chapter is regression models, chapter 4. Regression is one of the most widely used statistical analysis technique, and we have two kinds of regression analysis: simple linear regression and multiple linear regression. So it's simply the difference is how many x variables we use. Okay, we have a y variable that needs to be predicted, so which is like demand or some value that we want to forecast for the future. So that's your y, and it's also referred to as dependent variable or response variable. Okay. And we want to predict that y using an x variable. Okay, and that is called independent variable. Now, if you have only one x to predict y, then what we have is a simple linear regression. But if you use multiple x's, okay, for example, you want to predict demand for the product, and you want to use only the price of the product to forecast the demand, only one x, then we have simple linear regression. But if you want to include price of the product, how much we spend on advertising, and what is the competition price, and what is the inflation rate, what is the unemployment rate, and so on and so forth. When you have multiple x's, then we have multiple linear regression. Okay. So here is the chapter outline. So we'll start with a scatter diagram and understand the basic concepts, and then we'll do simple linear regression and go through the topics in the simple linear regression, and then we will look at multiple linear regression and go through the topics, and then how to use the linear regression modeling methodology to fit nonlinear equations. Okay, so that would be the last topic. Okay, regression analysis is a very useful tool, and it's often used in forecasting. Okay, simple linear models, only two variables, one y and one x. Multiple is one y and many independent variables. Okay, so we have dependent variable. Okay, that's your y, and then you have it's also called response variable. Okay, independent variables are explanatory variable or predictor variable. These are interchangeable names. Okay, with these you're trying to predict the dependent variable. Okay, scatter diagram is useful when you want to look at the relationship between y on the y-axis and one x at a time. Okay, if you have multiple x's, you have to use one x at a time. But if you have only one x, of course, there is just one x. So let's look at an example. Suppose we have the AAA construction renovates homes. So we have the sales of AAA, all right, and the local payroll. Sales is in $100,000, and the local payroll is in $100 million, right? So now, obviously, we want to use local payroll to predict what the sales will be. We want to forecast sales based on, so this is an important point because you have to make sure that you make the selection properly. If you identify the variables backwards, then the whole process, the whole analysis is going to be wrong. So you need to critically think about this. Why would you want to predict local payroll unless you're a AAA construction company, then your interest is in predicting the sales of your company. So that would be your Y, and payroll is in X. Now you plot that payroll in the x-axis and AAA sales on the y-axis, then you get something like this. Okay, and obviously it's not going to be on a perfect straight line because there are some random variabilities going on with that we have not accounted for. So now the idea is to fit a line through these points. So which will be like the equation will be like an intercept. We'll call that b sub 0, and then slope we call that b sub 1 times x. So we want an equation for predicting y that would look something like b sub 0, a value for b sub 0 plus a value for B sub 1 times X, where X would be the payroll in $100 million. So now how do we come up with this line? If you have only 2 points, of course you know how to develop that equation. But when you have multiple points, how do you come up with the line, and what is the criteria for deciding the best line that you can come up with? So this is the line, this is what the line is going to look like. Okay, y hat, that's our predicted value of y, is b sub 0 plus b sub 1 times x. Okay, we'll come to this slide in a little bit. Okay, so now what we're going to look at for the criterion for deciding what the best line is that we're going to look at what is the distance between the point and the line. Okay, so like here, so that's our y, actual y, and this is the line y hat. So this distance here is what we call as the error. Okay, this point deviates from this line by that amount. We'll come to the other things later on. Okay, right now let's focus on just this, y minus y hat. Okay, and you have y minus y hat for each and every one of these lines. Some of these y minus y hats are negative, some are positive. So these differences, how far away these points are to the line that we are trying to fit, okay, and that distance is the error. Okay, some are positive, some are negative. So if you just simply find an average error, the average error will turn out to be 0 for whatever the line may be. So we don't want that. So what do we want to do? Well, we don't want the positives and the negatives to get cancelled out each other. So there are a couple of ways in which we can proceed. One is to take the absolute value and add them up. Okay, but that doesn't have well, there are some issues with that. We can't derive formulas when you have a non-linear function like that. But it is a lot easier to handle mathematically if you square these error values and sum them. So then you get sum of squared error. Okay, so here is the actual value minus the predicted value, which is the line, okay, y hat. So the difference y minus y hat is our error, and you square that error and add them up, you get sum of squared error. All right, so now our task is to find the y hat, that is b sub 0 and b sub 1, in such a way that sum of squared error is minimized. So regression analysis minimizes the sum of squared errors, and that's why it's called least squares regression. So we can now, using calculus, we can derive a formula. So what b sub 0 value and b sub 1 value for y hat will give you the least possible value for the sum of e squared, the sum of squared errors. And it turns out that when you use calculus and derive the formula, this is the formula you end up with. Okay. B sub 1 is given by the sum of x minus x bar times y minus y bar in the numerator, and in the denominator sum of x minus x bar squared. That will give you the b sub 1 value, and b sub 0 is y bar minus b sub 1 times x bar. So if you use these two formulas to find y hat, then the line that you will get, okay, so that this line that you get with those formulas is guaranteed to give you errors that are, when squared and summed, will be the least possible amount. Okay, and that's why it's called least squares estimate. And let's look at a numerical example next.